Okay, so today we're going to do a new chapter called Improper Integrals. Okay, so this will be the last bit of integration that we're going to do. The remaining parts of this semester will be on applications of integration. So if you have a look at the scope, you'll see this is the last bit of integration. Then the rest is applications. So finding the length of the curve, area of a surface, volume of a shape, all of that will be applications of everything that we've done so far. Okay, so let's get started with the improper integrals. So improper integrals is split into two types. So we have a type 1 improper integral and a type 2 improper integral. So we're going to follow the convention of the textbook with what type 1 is and type 2 is. If you look online with YouTube or other notes, maybe they swap the two types. So just be careful, what we call type 1 and type 2. Other places might swap those. Okay, so just be careful with that. Okay, so type 1. Okay, so again, type 1, this is what the textbook calls type 1. This is when we have an infinite interval. Okay. So what do we mean by an infinite interval? It means if we have the interval a comma b that we're integrating over, either a is infinite, b is infinite, or both of them are infinite. So it will be something like this. We have the integral from a to infinity. So the top part is now infinite. Or we have where the bottom part is infinite. Or we have a case where both the top and the bottom are infinite. Okay, so if you see any of these three cases, we're dealing with a type 1 improper integral. Okay, so how do we deal with these? So let's look at the first one. So since infinity is, not a number, right? So we can't just evaluate the integral and substitute infinity. That doesn't work. So instead, we're going to replace the top bound with some variable. Let's call it t. We're going to do the integral with t, and then right at the end, we're going to have the limit as t goes to infinity. Okay, so that saves us from trying to substitute infinity. So here, when we write the integral from a to infinity, f of x dx, what we mean by this is the following limit. Limit as t goes to infinity. So we know how to do limits like that. Then we have the integral from a to t, f of x dx. Now this part's in blue here. This is easy to do, right? We're just going from a to t, f of x dx. We know how to deal with those. Okay, we've done all of the integration techniques, so that's easy to do. Once we get our answer, we then take the limit afterwards. Okay, so again, that saves us from trying to substitute infinity. So number one, we do the integral, the definite integral with t. With t. And then we take the limit as t goes to infinity, and then we check if that converges or not. So limit t goes to infinity. Now, if this limit exists, then we have a nice number for the integral. If the limit doesn't exist, well, then the integral doesn't exist. Okay, there's no number we can put for that. So if the limit exists, then the integral exists. Okay. So there's some area, the area under the curve, there's some number we can put to it. If this limit doesn't exist, then the integral doesn't exist. Okay, so if the limit does not exist, then the integral does not exist. Right, that just means we can't calculate the area. So the area under this curve, that will be infinite. So you can't put a number for that. Okay, so that's the general idea that we're going to follow. Very simple to do. So let's have a look at some examples. So number 1. Okay, so we have the integral from 1 to infinity 1 over x squared dx. Okay, so we can put a little sketch to this to see what this area is going to look like. So here we have the following picture. So 1 over x squared will look something like that. Okay, so we're just looking at the positive part because it's from 1 to infinity. So let's say 1 is over here. So the area is everything to the right of 1. So we'll put that in green here. It's all of this area here. Yeah, but the function goes to infinity, right? Okay, it goes all the way to infinity, and it asymptotes to y equals 0. So the question is, if we go all the way to x going to infinity, does that give us a finite area? So is this area finite? Okay. And we'll see for this example, that area there is finite. There is a finite number for that. So even though the function goes all the way to x equals infinity, x to infinity, that green area is still finite. Okay, so what do we do? Well, this top bound here is infinite, so we're going to replace that with t. We're going to do the integral as normal with t, and then we take the limit. So let's do that. So limit t goes to infinity, integral from 1 to t, 1 over x squared dx. Now, for now, we ignore the limits, so forget about that. We do the definite integral as normal. Once we're done with that, then we take the limits. So this is going to be the limit. T goes to infinity. Again, we do this as normal. So this will be minus 1 over x from 1 to t. Then we can substitute our bounds. So this will be the limit as t goes to infinity. If we substitute t, we get minus 1 over t. Then we get a minus and a minus, so that will be a plus 1. Okay. Now, once we're done with the integral, then it just becomes a limit problem. Right? We did lots of those last year. Right? Limit laws, squeeze theorem, L'Hopital's rule, all of that stuff applies here. So let's just make a little note so you don't forget. So limit laws, squeeze theorem, L'Hopital's rule. Remember those from last year when we did the limits? So all of that applies now. So whatever limit we get, you're going to be using something like that. Okay. So depending on what limit we get, you might be needing L'Hopital's rule or the squeeze theorem or something like that. But we covered that last year, so you should be fine. A little bit of revision there. This limit's very easy. So t goes to infinity. The first term goes to 0. Yeah, t goes to infinity. 1 over t, that goes to 0. So we're just left with 1. So since the limit exists, we got an answer of 1. It means the area under the curve is also 1. The limit exists. So L equals 1, which means that green area that we shaded in earlier, that green area is 1. Okay. So we see we do have a finite area. Okay, any questions for this first example? Okay, pretty easy warm-up problem. So number 2, we have the integral from 1 to infinity, 1 over x dx. So again, we can draw a picture of this. So 1 over x, that looks something like that. And we're going from x equals 1 all the way to infinity. So the area we're looking for is this part over here. Okay, and again, we're asking, is the shaded area finite or infinite? Yeah, so let's check. So we're going to do the same thing as before. So we have infinity at the top. We're going to replace that with t, do the integral as normal, and then we're going to take the limits. Okay, and again, this integral in blue, there's no issues with that, so we forget the limits. We do this integral, it's just a definite integral, easy enough to do, and after all of that's done, then we take the limits. Okay, so this is going to be equal to the limits, t goes to infinity. Yep, then we do the integral, so 1 over x, that becomes, yep, yeah, natural log of x from 1 to t. Okay, then we substitute and then finally take the limits. Okay, but the natural log of 1 is just 0, so that can go. So we have the limits as t goes to infinity, natural log of t. Does this limit exist? No, no, it doesn't. So this limit doesn't exist, which means the integral doesn't exist. Okay, there's no finite area under that curve. Right, D and E does not exist, okay? Therefore, that area is infinite. Yeah. Any questions for this one? All good. Okay. Number 3. We have the integral from 0 to infinity, x e to the minus x dx. Okay, so now we see the integral is not so easy as before. We've got x e to the minus x. So what do we have to do to solve that? What's that? Product rule. No, 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 no. We covered it a couple weeks ago. You got a product of two things. Yeah, your u, your dv. Remember that? Yeah. Okay. Integration by parts. So we're going to call the top part t, do the integral, but now we need integration by parts. Then right at the end, we're going to take the limit. And we'll see when we have to do the limits, we have to use L'Hopital's rule. Okay, so quite a lot going on for this problem. Okay, so first thing, let's replace the top part with t and then put the limit. So now we have this integral in blue there to do. So we forget the limit, we just do the integral as normal, and then right at the end, we can take the limits. Okay, so let's just do this on the side here. So, oops. So we have the integral 0 to t, x e to the minus x dx. So we're going to treat it just as a normal integral and then do the limit. So we've got this. What's u going to be? x, good. And dv? Yeah, all that other stuff on the side. Okay, so here we have du is dx, and v, we take the minus down, so it will be minus e to the minus x. Okay, then we use that formula we know now. So integral u dv, uv minus integral v du. Okay, so that will be uv. Okay, and we've got the minus sign from v, from 0 to t, minus the integral v du. Okay, and again, this goes from 0 to t. Okay, so now we substitute. So for the first bracket there, if we put in t, we're going to get minus t e to the minus t. And if we put in 0, we've got an x in the front, so that just makes everything 0. And then for the next one, we got a minus and a minus, so that will be a plus. Yeah. And then we just have that integral to do there. So this will be minus t e to the minus t plus. Okay, same thing as we did before. The integral, we take down a minus. So this will be minus t e to the minus t plus. Let's substitute t. So we're going to have a minus e to the minus t. Then a minus and a minus, that will be a plus. So we have a plus 1. Okay, so let's just rewrite this a little bit. So we have 1 minus t e to the minus t minus e to the minus t. Okay. Everyone okay with the integration by parts? From the AB bound here. So e to the minus t, that's our first one. And then e to the 0 is 1. And then the minus 1, we get a plus 1. Yeah, because FA minus FB. Yeah, please remember your minus signs and all that. Any other questions? All good. Okay, so integration by parts. So you can already see there's a lot going on here. So it's improper, we've got integration by parts to do. Now when we do the limit, we'll see we have to do L'Hopital's rule. Okay, so quite a lot going on. So this will be the limits as t goes to infinity of all of this that we got here. So 1 minus t e to the minus t minus e to the minus t. Okay. So the 1 is just a 1. We don't have to worry about that. The second one, that's a little bit of a problem. So when t goes to infinity, we're going to have infinity times e to the minus t goes to exponential goes down to, the exponential when t goes to infinity, e to the minus t will go to 0. Yeah, please remember your pictures. Okay, goes down to 0. So what do we have? We have t, which will go to infinity, e to the minus t, that will go to 0. So this over here becomes infinity times 0. Remember your indeterminate forms? No? Hands up if you forgot your indeterminate forms. Okay, you have to be honest. Either I go through it again or I don't. So please, hands up. Okay, thank you. If you keep your hands down, I'm just going to carry on going, thinking you know it. Okay, so we'll do some indeterminate forms, but please keep an eye out for those, right? When you do these limits, you can't just say, oh, limit doesn't exist, infinity times 0, right? You need to do these properly. So infinity times 0, that's an indeterminate form. Okay. So when we have an indeterminate form, we know we have to do that bit of algebra, then we have to do L'Hopital's rule. Okay, so let's do that on the side. So L'Hopital's rule. Okay, so remember, L'Hopital's rule, that works for limits where we have a numerator being infinity and a denominator being infinity. Remember that? Okay, so we have some sort of limit. Yeah, I can't reteach all of L'Hopital's rule. I have to start somewhere. So we have something like this. You do the limit. We have infinity at the top, infinity at the bottom. Then we can do L'Hopital's rule. But over here, we've got infinity times 0. That's not going to work. So what we need to do is rearrange this so we get infinity over infinity. Then we can do L'Hopital's rule. So we've got t, e to the minus t. This is infinity times 0, indeterminate form. But e to the minus t, we can put that in the denominator. So this will become t over e to the t. Everyone see that? So now the top part, when we do the limit, the top will be infinity. The bottom will also be infinity. So now we have infinity over infinity. Now we can use L'Hopital's rule. Okay, so what is L'Hopital's rule? Well, we want the limit of this. So the limit t goes to infinity, t over e to the t. By L'Hopital's rule, this is the same as the limit where we do the derivative on the top and the bottom. So L'Hopital's rule, this tells us this is the same as the limit t goes to infinity, d by dt of the top, d by dt of the bottom. Okay? And if this gives us an answer, then that's the limit value. If it is still infinity over infinity, we do L'Hopital's rule again. And then maybe again and again until we get some answer. So let's do the derivative. Then we take the limit and see what we get. So this is going to be the limit. T goes to infinity. The derivative of the top is 1. The derivative of the bottom, that just stays the same. Now, when t goes to infinity, the bottom goes to infinity, the top stays 1, so this goes to 0. And we don't have to do L'Hopital's rule again. Once we know the limit value, we stop there. Okay, so after L'Hopital's rule, we see that this middle term, the pink one here, that will be 0. And the third one, we know from our graph, that will also be 0. Okay. So we're left with just 1. So therefore, the integral from 0 to infinity, x e to the minus x, it's just 1. Right? We showed the limits exist, so this integral is 1. Okay. Any questions about the L'Hopital's rule part? Okay. Please make sure you know how to do L'Hopital's rule. Okay, when you do these limits at the end, guaranteed there's going to be something with L'Hopital's rule. Okay, any questions for that before we move on? Oh, good. Okay. Number 4. Just also, if you need more revision for L'Hopital's rule, you know, the lecture videos from last year are still up. Also, the MATH160 page is open for guests. So if you go to this year's 160 page, you'll see we're doing L'Hopital's rule there as well. So you can look at those notes. Okay. Number 4, we have the integral from minus infinity to infinity of 1 over 1 plus x squared. Okay. So here, the top and the bottom are infinite. So in this case, what we're going to do is split this into two parts, where one of the parts is going to look like this, okay, from a to infinity, and the other part is going to look like this, from minus infinity to b. So we're going to split it up, do them separately, and then add the results together. Okay, the problem is, with both of them being infinite, you can't say that the top is t and the bottom is minus t, but that doesn't work. Okay, so we need to split it into two problems separately. Okay, so how do we split it? Well, this is an even function, okay, 1 over 1 plus x squared. So we can split it into the negative part from minus infinity to 0, then the positive part from 0 to infinity. Right? If it's even, we can split it like that. If it's not even, you need to think a bit more about it. So this will be the integral from minus infinity to 0 plus the integral from 0 to infinity. Okay, again, because it's even, it gives us a now splitting. If it's not even, you need to think a bit about that. Okay, so let's call it number 1 and number 2. We'll do them separately and then add it up at the end. Okay, so let's do number 1. So the bottom part is infinite, minus infinity. So we're going to call that t. So this will be the limit as t goes to minus infinity, integral from t to 0, 1 over 1 plus x squared. Okay, then we ignore the limits, do the integral, and then take the limit at the end. Okay, integral of 1 over 1 plus x squared, arctan. Okay, 0 and t. So this will be the limit. T goes to minus infinity. Arctan at 0. What's tan of 0? 0, yeah. So arctan of 0 is 0. Minus, and then we substitute t. Okay, so the 0 we don't have to worry about. The minus we can take out. So we just have the limit of arctan. So t goes to minus infinity. Arctan will then go to? Where will it go to? No? Think about the picture. Remember we drew those pictures last year with the these inverse functions? So tan, so how does tan look like? And then you flip it over. Remember the inverse functions? Go look back in your books. You've got them with you. So the inverse functions, right? We have a function. We want to find the inverse. You flip it over. Hey, come, you have to know these functions, right? Yep. Pi over 2. No, we're going to minus infinity. It'll be minus pi over 2. Yeah. Okay. So it looks something like this. So here is minus pi over 2. Here's pi over 2. Right? It's the flipped over version of tan. So tan looks something like this. Right? Tan looks like that on the right. You flip it over, you got arctan on the left. Okay, so we get minus pi over 2. We've got a minus in front, so minus minus pi over 2. That will be pi over 2. Okay, but that's only half of it. We did integral number 1. Now we need to do integral number 2 and then add it up. Okay, so this will be limit t goes to infinity, integral from 0 to t, 1 over 1 plus x squared. Now the top goes to infinity, so we put the t at the top, then we take the limit. So this will be the limit. T goes to infinity. Again, integral 1 over 1 plus x squared. That will be arctan from 0 to t. Just remember your bounds, okay? It will be different for this one. So the previous one, we went from minus infinity to 0. So t was at the bottom. This one is from 0 to infinity, so t is at the top. Okay, two separate integrals. Don't mix them up. So this will be the limit. T goes to infinity. First bound we put in, so arctan of t minus arctan of 0. 0, yeah, we know that now. So when t goes to infinity, arctan goes to, we go back to the picture. So t goes to infinity, the y value will be pi over 2. Okay, so this will be pi over 2. So we see the first integral was pi over 2. The second integral was also pi over 2. So both of those limits exist, so we can add up the results, and we get that the integral from minus infinity to infinity, 1 over 1 plus x squared, will be pi over 2 from the first limit, plus pi over 2 from that second limit we got there. It's just pi. Yeah. Any questions for this one? All good. Okay, two homework problems for this. So number 1. Show that the integral from 0 to infinity of x to the n e to the minus x. So here n is some integer. Okay, so it's not any real number, it's an integer, is equal to n factorial. Everyone remember the factorial? 1 times 2 times 3 times 4 all the way up to n factorial. Okay, so show that. You're going to have to use some integration by parts with this. Okay, so we've got a polynomial parts. So there'll be u, ev, everything else. A little bit of L'Hopital's rule. You got your answer. And then number 2. For which values of p does the integral from 1 to infinity 1 over x to the p dx converge? Okay, so when we say it converges, it means after we do all of the limits and everything, we get some number. So the limits exist. So limits exists and is finite. Okay. So for what values of p? So there can be any real number, okay, not like an integer. So for what values of p will that converge? Okay, so there's some interval where it does not converge, it goes to infinity. There's another interval where it does converge. Okay, so find where it does converge. Any questions for these two homework problems? Oh, good. Okay, so that was type 1 improper integrals, where you have that infinity in the bounds. Type 2 improper integrals is a little bit more tricky. Okay, so type 2. Vertical asymptotes. Okay. So for type 2, somewhere on the interval from A to B, there's a vertical asymptote somewhere there. So the asymptotes can either be at A, there's an asymptote there. It can be somewhere in between A and B, or it can be at B. Okay, so it's somewhere on that interval. So I can either be like this. Okay, so we want this area here from A to B, but there's an asymptote at A. Okay. Or it could be something like this. So again, we're going from A to B, and there's an asymptote somewhere in between. Okay. Or the asymptote can be at B. In other words, somewhere on that interval from A to B, we have an asymptote. So in these cases, there's one. There might be more, okay, but there is some asymptotes on that interval. So we have the integral from A to B, f of x dx, where we have at least one asymptote. Again, there could be more, but there's at least one. At least one asymptote on the interval AB. Now, the issue with these is that just by looking at the integral, like very quickly, it's very difficult to tell if it is improper or not. Now, the issue is, say in the test, I give you 5 mixed integrals. Maybe 4 of them are like what we covered before, there's no issue. Maybe one of them is an improper integral. You need to spot if it's improper or not. So the question won't be, these are improper, evaluate them. The question will be, evaluate the integrals. You need to spot whether it's a normal one, like we covered before, or if it's improper. Okay, that's up to you to spot. For example, number 1. We have the integral from 2 to 5, 1 over root x minus 2. Something like that. Now, I could just give you this. This looks like something we've done before, right? You know, u substitution in the bottom. We have u to the minus 1/2, right? Easy stuff. No, you get 0 if you treat it like that. Because your answer will be something completely wrong if you don't treat it like an improper integral. Yeah, so please be very careful with these. It looks very innocent like this. This is actually an improper integral, and we have to do this whole limit setup like we did before. Okay, so again, please be careful. So the reason is, look at the lower bound at 2. What happens to that bottom part when x goes to 2? The bottom becomes 0. We have 1 over 0. That's a problem. We cannot just substitute 2, right? There's a problem there. So here, it looks something like this. So at 2, there's an asymptote. So from 2 to 5, we have this. So we can't treat it as a normal integral, right? At 2, there's an asymptote there. You can't just substitute 2 into this function. So since 2 is an issue, we're going to replace that bottom bound with t, and then we're going to take the limit as t goes to 2. Okay, that fixes everything. So here, this is going to be equal to the limit as t goes to 2 but we must be careful. We're going from 2 from the right. So it will be limit t goes to 2 plus. Okay, we can't just have limit goes to 2. That doesn't work. We need to go 2 plus because we're on the right-hand side. Okay, then it will be the integral from t to 5. Then we have the normal thing, 1 over root x minus 2 dx. Okay, so please be careful with this limit here. Okay, so next we ignore the limit, we do the integral as normal, and then take the limit at the end. And you'll see this 2 plus is very important for the ending. So this will be the limit as t goes to 2 plus. Okay, we do this as normal. Integral t to 5. We can write this as x minus 2 to the minus a half. Okay, we treat it like a normal integral. I'll let you fill in the details, but same thing as we did before. Add 1 to the exponent, divide by that. Okay, normal integral. So if you need to do a u substitution, you fill in the details on the side. So we have limit t goes to 2 plus. This will be 2 root x minus 2. Okay. Now we substitute. So if we put in 5, that's not an issue. 5 minus 2, that's 3. No issue there. So this will be 2 root 3. No issue. Minus 2 root, and now we substitute the t. And this is where this part here is important. So here we're taking the limit as t goes to 2 plus. So we are saying t is greater than 2. What happens if we substitute something that is less than 2 into that root? It will become negative on the inside. You can't take the root of a negative. So you don't have an answer, right? So that's why it's important to be careful with this limit. If you're not careful with it, you put something less than 2, right? If you go from the left side, now it doesn't exist, right? Root of a negative. Can't do that. Okay, so very important that we put a positive value under the root. So this bottom part must be positive. Okay, that's why we put the 2 plus. So let's do that. So this is going to be 2 root 3 minus. Okay, now we put in 2 plus, so everything's fine. What does that become? In the limits, t goes to 2, 0. Yeah. Okay, so we get 2 root 3. Okay. So again, this looks very similar to what we did last time with the u substitution, but you see all the other work we have to do, right? With the limits and the asymptotes and all of that. Now again, in the test, not this test one, the next test 2, I'm going to give you a list of integrals to do. I'm not going to tell you which ones are improper and which ones are not. Okay, so under the u substitution section, you'll get this. So you do all of your u substitution, but it's also improper. You need to spot when to do that or not. If you cannot spot that it's improper and you get the wrong answer, you just get 0. Okay. So please be very careful on spotting if it is improper or not. Okay. Again, for the test 2, June test, test 3, test 4, all of this comes up. Okay. Any questions before we move on? All good. Okay. Let's do number 2. Okay. Now this one is even more dangerous than the previous one. So here we have the integral from 0 to 3, 1 over x minus 1. Okay, now it looks simple, right? 1 over x minus 1. Let's do it 2 ways. First, we're going to do it as if you forgot improper integrals, and you just do it normally in the test. Let's see what we get. Then we do it the proper way, and you'll see it's completely different. Okay, so here we do it the wrong way. Just to show you how much you can actually mess up with these. Okay, so let's do it the wrong way. Can you see the red? Can you see that out? Okay, so that's the wrong way. So this is going to be the integral from 0 to 3, 1 over x minus 1 dx. You think, oh, very easy. 1 over x minus 1, that goes to? Integral becomes natural log. Okay, so you think, oh, easy, I know that's no problem. Right, you put your absolute values, you think everything's fine. Let's carry on. So let's put 3 in. So 3 minus 1 is 2. Natural log of 2. Easy, no issues, right? Minus. We put in 0. We get the natural log of 1 because of the absolute value. Natural log of 1 is 0. Easy answer. Natural log of 2. Okay, I'm getting my 5 marks. I move on. Okay, let's actually see what the problem is now. So 1 over x minus 1 on the interval from 0 to 3. That bottom part has an asymptote, right? Where's the asymptote? If we look at the bottom part. At 1. So from 0 to 3, that includes 1, which means it includes the asymptote. So if we draw this picture here, draw the picture. So at 0, it's fine. There's no issue, right? Because if we put in 0, we just get the function at 0, -1. So there's no issue there. So we're somewhere over here. And at 3, half. So we're somewhere over here. Right? Or something like that, right? So if you only look at the endpoints, you think, oh, there's no issue. At 0, it's just -1, that's fine. At 3, it's going to be a half, that's fine. But somewhere in the middle there is an asymptote. So going here, we go down, and over there we go up, and there's an asymptote line in the middle. That's going to be a very big problem. So what we're going to do is split this into 2 integrals, one for the left-hand side of the asymptote, one for the right-hand side of the asymptote. So we're going to have this integral, integral number 1 on this left side, integral number 2 on the right side. Okay, and we're going to see what does this give us. If the sum of the 2 gives us this natural log of 2, then everything's fine. We'll see that's not the case. So let's do integral number 1. That's the green one. This will be the limit as t goes to 1 minus, because we're on the left side of the asymptote, integral from 0 to t, 1 over x minus 1 dx. Okay, so again, this asymptote at t, we're on the left side, so it will be 1 minus. So this will be the limit as t goes to 1 minus. We do the integral as normal. So that will be natural log x minus 1. Everything's fine. 0 to t. If we put in t, we just get t minus 1. So no issue there. And if we put in 0, we just get natural log of 1. That's 0. So that's all fine. So we're going to leave it like that for now. Let's have a look at the other one. So integral number 2. That's going to be the limit as t goes to 1 plus. Because now we're looking on the right side. So it's 1 plus. So this will be the integral from t to 3. Okay, because we're on the right side. This blue part from 1 to 3. Okay, 1 over x minus 1 dx. Okay, same thing as before. We do the integral, take the limits, see what we get. Okay, limit t goes to 1 plus. Okay, everything's fine, natural log from t to 3. Now we can put in 3. That would just be the natural log of 2. Everything's fine with that. Minus the natural log of t minus 1. Now, what do we want to do? We want to add these two together, right? We want to take the answer from 1 and add it to 2. Right, so we want to try add these two limits together. Now, can we do that? Remember your limit laws from last year? So if we have the limit x going to a, f of x plus g of x is equal to the limit x goes to a, f of x plus the limit x goes to a of g of x. Right, that was like the first limit law we wrote down. But there was a condition. You can't do this all the time. What is the condition for us to split up that limit? There was one condition. So I wrote the limit law and I said we can only do that if something. What was it? Now, I warned you guys last year, right? We did the work and I said, don't forget it. We'll see it next year, right? Now we're seeing it this year. Okay. So I got a limit of the f plus g and I split it up into two separate limits. There's a condition. We can't just do it whenever we like. When can we do it? When can't we do it? What's the condition? Okay, who wants 2 extra points in the next quiz if you get it? Okay, first one to get it, you get extra 20% for the quiz. What's that? Okay. Anyone else? 20%, it's quite a lot for just looking back in your book to see what the answer is. Okay, let's make it 30%. No. Okay, let's make it 50%, but you got 10 seconds. 10, 9, 8, 7, 6, 5. Just put your hand up. 4, 3. Oh, who said that? Limit exists. Very good. What are you going to say? Come, you know me now. Give points for nothing. Okay. Yeah. If those limits exist, that's the condition. So these limits must exist. Right, we can't just add them if the limits don't exist. So the limits must exist. So let's check. We're trying to add these two, to get our answer. Let's check the first one, and then we'll check the second one to see if they actually exist. Can we add them together? So the first one, t goes to 1 minus. What does that inside become? No, 1 minus 1 on the inside? 0. Natural log of 0? goes to minus infinity. Right? You know your graph. Natural log goes down to minus infinity. Okay, let's look at this. So this one doesn't exist. First one doesn't exist. Let's look at the second one. T goes to 1 plus. This inside part will go to 0. Natural log of 0. That goes down to minus infinity again. The limits do not exist. Right? So that means this integral does not exist. So the limits do not exist. Therefore, the integral does not exist. You see how dangerous this thing is. So let's go back to the top here with this wrong way. So say I give you this question out of 3 or 4, whatever it is. Okay, so now you think, oh, very easy. I'm just going to put natural log, put in 3, I get natural log of 2. What are you going to get for that? 0. You're telling me it's natural log of 2, but the limit doesn't even exist. You're putting funny numbers down. That's not right. Okay, so please be very careful with what these improper integrals look like. So just because it looks all innocent, 1 over x minus 1 looks perfectly fine, you need to be aware of those asymptotes. Either the asymptote is at the beginning or the end, or even more dangerously, somewhere in between. You have to check them. Right? For class test 2, say I'll give you 5 questions. Maybe 1 of them is improper like this. Maybe 2 of them is improper. I'm not going to tell you. Maybe none of them are improper. Right? So I'm not going to trick you. I'm telling you some of them will be improper. Maybe 1, maybe 2, maybe all of them, maybe none of them. You need to be able to spot it. Yeah. You need to be very careful and look for those asymptotes. So whenever you have 1 over something, you look at that bottom part. So here, where's the asymptote? At 1. So the bounds is from 0 to 3. That includes 1. So it becomes improper. Yeah. So you look for the asymptotes in the bottom here. Look for asymptotes. So here we have x equals 1. That is included in the bounds from 0 to 1. So this is somewhere from 0 to 3. That means it's improper. Yeah. Yeah.
Can go that is proper. Or means we have a question like that and it has bounds. It doesn't have bounds.
Yeah. Only if there's bounds. Yeah. If there's no bounds, you just do it as normal. If there are bounds, you need to be careful. Okay. Any other questions for that? Okay. So let's give you one for homework that's similar to this one. So integral from minus 1 to 2, 1 over x, x minus 1. Now, if we ignore the bounds there, that's a partial fractions question, right? Right, we did that last week. So it's partial fractions. So we know we're going to have to do some partial fractions with it, but we must be careful. That bottom part could be 0 now. So where are the asymptotes for that? There's 2. X equals 0. X equals 1. Are those asymptotes included in the bounds? Yes. 0 is between minus 1 and 2. 1 is also between minus 1 and 2. There are 2 asymptotes between the A and the B. So it's improper. So improper. So we have 2 asymptotes. X equals 0 and x equals 1 on the interval minus 1 to 2. So as soon as we see those asymptotes on the interval, you need to treat it like an improper integral. If you don't, your answer is going to be like what we had before. Completely wrong. Yeah. So for homework, do it with the improper integral way. Then do it the wrong way, like we had before, and see where does it go wrong. Okay. So if you do it the wrong way, you get some number, all nice and good. Do it the improper way and check. Yeah, there's going to be something wrong between the two different ways. Like we saw for this one, the problem was here, where we had to add these limits. Okay. So homework, please check that. So that was homework number 1, and then homework number 2. We have the integral from 0 to 1, natural log of x dx. Okay, here we also have an asymptote. Where is it? The asymptote for the natural log? At 0? Is 0 somewhere on the interval? Yeah, at the bottom there. We got the 0. So this is also improper. Okay, so we have one asymptote at x equals 0. Okay, so I've told you where the asymptotes are for those two. So do the limits, as t approaches the asymptote, see what you get for the second one. Okay, you should get -1. So this does exist. Okay, it's not like the other one. This does exist, but you need to be careful with the limits. Okay, so check this should be -1. All right. Any questions for this? All good. Okay. Last thing for today. The comparison test for integrals. And just a note before you decide to learn and forget within a week, we will see this later on for series convergence. So I'm warning you now, I'll put a little note there. We will see this again later. So please do not do the learn, do the test, forget thing that you guys do. Okay, so big warning here. We will see this again for series convergence tests. Okay. So series convergence tests, don't worry about that for now. We'll get that later. But when we do get to that chapter and I say, flick back to this, please make sure you have this with you. Okay, so what is this comparison test? So let's say we have two functions f and g. The two functions such that we have 0 is less than or equal to f and is less than or equal to g on their domains. Okay, so they must both be positive, and g is larger than f. Okay, but they have to be positive. That's very important. So it looks something like this. Okay, so we have 0 right there. Then in between there, we've got f, and above we have g. So it must look like this. Okay, so what does the comparison test tell us? It says that if we start here at sum a, and we calculate the area to the right, so all of that area on the right-hand side, we have two statements. So number 1, if the integral from a to infinity of g, which is the larger one, converges, then the integral from a to infinity of the smaller one also converges. Okay. And here's where the ordering matters. Statement number 2. If the integral from a to infinity of the smaller one, you see how the ordering swaps there. Okay, if we have the integral from a to infinity of the smaller one diverges, then the larger one will also diverge. Okay, now please remember the ordering. Okay, so we've got f being the smaller one and g being the larger one. If you mix those up, you get all of these statements mixed up as well. So f is the smaller one, g is the larger one. Then the integral of the larger one converging means the smaller one converges. So larger one converges means the smaller one converges. Now for the second one, we swap it around. If the smaller one diverges, then the larger one diverges. Okay, they swap. Okay. Does everyone see that? Okay, please do not mix up these two. Okay, so we got 2 examples just to show how this works. In the tutorial, there's quite a few more for you to look at. So example. So number 1, show that the integral from 0 to infinity of e to the minus x squared converges. Okay, so that gives us the hint as to what we need to do. So we've got this integral. This one we cannot do just by ourselves, right? Integral e to the minus x squared. There's no u substitution you can do. There's no integration parts by parts you can do. There's nothing we can do with that. So to show that it converges, what we are going to do is show that there is some larger function that also converges. Then that means the smaller one converges. Okay, so this here we're going to call f. That's going to be our smaller one. What we're going to do is find a function g that's larger. We're going to show that the larger one converges, which will be an easier integral to do. If that larger one converges, then the smaller one that's given also converges. So the idea, we're going to find g such that 0 is less than or equal to f, less than or equal to g, where the integral from 0 to infinity of g of x converges. Yeah. So if we can find a larger one that converges, then the smaller one converges, the given one, and we're done. Yeah, so that's the idea. Okay, so what can we do now? So let's try to find this g. What's giving us problems in this integral here is that exponent, that e to the minus x squared. Right? There's no u substitution we can do to get rid of that. So let's try something else to try get rid of that exponent. Okay, so what are we going to do? We're going to take our integral from 0 to infinity, e to the minus x squared, and we're going to split it up into 2 parts. We're going to split it into the integral from 0 to 1, e to the minus x squared, plus the integral from 1 to infinity, e to the minus x squared. Yeah, so we split it up. This first one here, from 0 to 1, this one automatically converges. There's no infinity anywhere, so no issues with that. This converges. Okay, no issue with the first one. The second one, we're going to try and make it simpler using that exponent. So notice that if we have x, this is going to be less than or equal to x squared for all x greater than or equal to 1. Does everyone agree with that? If x is greater than 1, then x squared is bigger than x. Okay, obvious. Now, what do we have in that exponent there? Do we have x squared or do we have minus x squared? Right, we got minus x squared. So we need to multiply both sides by a negative. So let's do that. Notice that the inequality flips, right, because of the minus. Now again, in the given question here, we have e to the minus x squared. Over here, we have minus x squared. So let's do e exponential on both sides. And we know that both of those are positive. So what do we have in the middle? E to the minus x squared. E to the minus x squared. That's our f, right? Okay. And this e to the minus x, we're going to call that g. Okay. So we have found a g that is larger than f on that interval. So all we need to show is that this integral of g converges. If the larger one converges, then the smaller one converges. So let's do that. So we have the integral from 1 to infinity, g of x dx. Yep, that's the larger one again. If the larger one converges, the smaller one converges. So the top is infinite, so it's a type 1 improper integral. So this is going to be the limit. T goes to infinity, integral from 1 to t, e to the minus x dx. Yep. Very easy to do. So let's do that. So we have the limit. T goes to infinity. This will be minus e to the minus x from 1 to t. We can substitute and then take the limit. Limit t goes to infinity, minus e to the minus t. And then we have minus and a minus, so that will be a plus e to the minus 1. Now, when we do the limit, e to the minus t, that will go to 0. So our answer is e to the minus 1. Now, it doesn't matter what number this is. All we need to show is that that limit exists, which we did. It's e to the minus 1. Okay, so the integral from 0 to infinity of our g function there. Sorry, this was from 1 to infinity. So from 1 to infinity of the g function converges. And like we had above here, if the g integral converges, then the f integral converges. And we're done. Okay. So instead of solving the more difficult problem of e to the minus x squared, okay, we found a larger function g where that one converged. So it means this one also converges. Okay. Any questions for this one? All good. Okay. So we got one more problem. Yeah. I repeat it. Yeah, sure. Okay. So we've got this large this function f, right? E to the minus x squared.
Convergence.
The limit exists.
Oh.
Yeah. Okay. So this integral, we want to show it converges. So when we do the limit with that infinity, it exists. But that integral we can't do, right? You can try. U substitution won't work. Our parts won't work. Nothing will work. Okay. So instead of doing that integral, we're going to look for a function g that's larger that does converge. We can show it converges. Okay. So we want to find this. So we need to find something that is bigger than e to the minus x squared. Okay, so how do we do that? Well, we start from the beginning. We know x is smaller than x squared. We know that, right? But this is not what we want. We want e to the minus x squared. So how do we get from here to here? Well, first we need to multiply both sides by -1 because this exponent is minus x squared. Okay? But we're still not done. That's not what we've got. That right-hand side needs to be e to the minus x squared. So we do the exponential on both sides. So that gives us our next step. Right? So now this middle one is f. This one is larger. That's what we wanted. We want a larger function, g. Right? Now we do the integral of g. If that one converges, then the smaller one converges. And that's all we did here. We did the integral of g. It converges, so f converges. Okay. Any other questions? Okay. Okay. Example 2. That'll be the last one for today. So we have the integral from 1 to infinity, 1 plus e to the minus x over x dx. Okay, so we have this integral. The question, show that it diverges. Yeah, and again, that's our hint, diverges. So let's go back to those two statements here. So we're talking about it diverging, so it must be statement 2. Statement 1 is about converging. The question said diverges, so we look at the second one. So what do we want? If f, that's a smaller one. If the smaller one diverges, then the larger one diverges. What do we want to show? We want to show that this one diverges. So we need to find an f which is smaller that diverges. Make sense? Okay, so this is our g. So we need to find the smaller function f 0 less than or equal to f of x less than or equal to g of x, such that the integral from 1 to infinity of the smaller one diverges. Then, if the smaller one diverges, then this one that we call g also diverges. That's what we want. We want to show that this g here diverges. Okay. So we won't go through all the calculations. That will be for homework. So, homework. Show that 1 over x, that's our function f, is smaller than that given function. Yeah. It's not too difficult to do there. So f over there, that's going to be our smaller function. 1 plus e to the minus x over x, that's g, that's the larger function. Okay. So let's do the integral for f and show that it diverges. Okay. So we did this one earlier today, so we'll go through it quickly. So we replace infinity with t and then take the limits. Okay, we ignore the limit and the integral will be the natural log. We can substitute t. So we get the limit, t goes to infinity, natural log of t. If we substitute 1, we get 0, so we just have this limit. Does this limit converge or diverge? It diverges. When t goes to infinity, natural log goes to infinity, this diverges. So we've shown that the smaller one, f, diverges. If the smaller one diverges, then the larger one diverges. Okay. Any questions for this one? Yeah. Oh, that's from over here. So this e to the minus x, right? That's our part that's giving us issues. What happens when x goes to infinity? E to the minus x will go to 0. So we're going to ignore that one. What's left over? 1 over x. Yeah. So when you're showing this over here, you'll use that. You'll use that there. So I'll give you a hint for this one. Be like that, right? Because in the limits, it goes to 0. So that's our starting point. Yeah. And then it's very quick to go from the hint to that final answer. Okay. Any other questions? Okay. So in the quiz and the test and all of that, it will be something like these two. So you'll get an integral, and it will be show that the integral converges. Then you look at statement 1. So you need to find something larger that converges. Or the question will be, here's an integral, show that it diverges. Then you need to find something smaller that diverges. Okay, that's what you would need to do for the two. Any questions before we go? Okay, so tomorrow we're going to be looking at the Laplace transform. If you are doing electrical engineering, please pay very, very, very careful attention to tomorrow's lecture. Okay, if you're doing electrical engineering, you will see the Laplace transform from tomorrow until you leave with your degree. Okay, it is used all over the place for your circuits and your signals. Okay, so again, electrical engineers here, pay very, very close attention to tomorrow's lecture. Okay, any questions before we go? All good. Okay, we'll see you tomorrow.